Pode ficar, William.
Okay.
So sorry. Ok. Boa tarde, bem-vindos ao ciclo de seminários do Observatório Nacional da Geofísica. Hoje nós temos um convidado lá do Canadá, o Anton Vetrov, que vai nos falar sobre os equipamentos de magneto telúrico, né, dar um update, contar a história e ver esses equipamentos mais modernos, né, e vai nos apresentar. O Anton é geofísico sênior da empresa Fênix Geophysics, que trabalha com instrumentação em geofísica em geral, não só em magneto telúrico, existem outros equipamentos de outras áreas também que eles trabalham. A representação deles aqui no Brasil também é feita pelo Carlos Guerreiro, que está trabalhando também na Fênix e faz essa representação junto aqui com a gente no Brasil. Muito obrigado por ter aceito nosso convite, Carlos. Anton, thank you very much for accepting this invite, ok? And a apresentação será feita em inglês por ele, e ele vai estar transmitindo para vocês. Vocês podem estar colocando seus comentários no chat ao vivo, pode ser em português, que eu vou estar traduzindo para ele no final da apresentação, e o William, que também está participando com a gente, vai poder exemplificar alguns termos mais diretamente do magneto telúrico. So, thank you very much, Anton, and the work is for you.
Okay. Hello, everybody. I'm sharing my screen right now. Turn off the camera. Start with the first presentation. Today we're going to talk about the magnetic tellurics and about the new equipment, about the data processing, and at the end of the presentation I'm going to show a couple case histories related to magnetic tellurics into the mineral exploration. The first presentation is about the equipment. I will start with several words about Phoenix Geophysics, who we are. Phoenix Geophysics is on the market of ground EM geophysics for last 45 years. We started back in 45 years ago, we started with ground IP methods, but in 1980, we built our first magnetic telluric station. This magnetic telluric station, because of the computers at that time, required 2 pickup trucks to be moved from side to side, so it was pretty large. Today we're going to talk about the 4th generation of equipment, which was recently released to the market in 2018. It's very compact and very convenient to use. Phoenix Geophysics for all those years has participated in all aspects of magnetic tellurics, starting from the field work, development of equipment, development of software, processing the data, logistics, data interpretation, 3D inversion, and more. Today, Phoenix Geophysics is a worldwide leader in magnetic tellurics equipment development. We have 1,000 systems all around the countries, on all continents, including Antarctica. Our approach to the new equipment a little bit changed than it was before. If you remember, some of you remember the old good days where the geophysics was to understand what this error reading is. Today, this is quite changed. Today, we believe that geophysics is mostly working with the data. Thanks to today's computation technology and new algorithms, new computer capabilities, This where we can spend most of the time interpreting the data, doing making the 3D inversions, modeling. So therefore, the field operation, even we very love the field operation, should take as less time as possible. The geophysics not in the field anymore. So the field should be very simple, very understandable, very convenient, and very fast. What means this means that the installation of the system, operation of the system, should be very understandable and simple. Should be, we'll say, a kid should be able to operate the system. And also the system should offer the possibility to record the data from the first time, because we all know that in the field we have sometimes to repeat the data. There are different factors which slowing down the data acquisition, such as environmental and external influences. But also one of the factors is we are all human. We make mistakes. We can forget something. We can turn on incorrect parameters, and this will require us to repeat the data. So today's equipment should eliminate this part of the human mistakes. So it should be very simple to operate, not sophisticated. So the simplicity of data acquisition minimizes the sudden mistakes during the field operation. And this allows to spend more time on geophysics today on working with the data. And at the end, the customer success is our success. So therefore, we try to do the best product for you, because if you are happy, we're happy too. Now we're going to talk about ultra wideband magnetic tellurics. First of all, what is ultra wideband magnetic tellurics? The physics is the same, and the operation is very similar. It's a lot of digging in the field. So the physics is the same. We work with the natural electromagnetical fields, which are provoked by lightnings and by the solar activity, which covers the range of frequencies that the lightnings, given the range of frequencies from 10 kilohertz down to approximately 10 hertz. And it's called audio magnetic tellurics because it's same frequencies as an audio signal. And the solar activity provides the range of frequencies from about 300 hertz and down way below the 1 hertz. And those parts are called magnetic tellurics and a long period. What we measure in magnetic tellurics, we measure two components: as a magnetic component and electrical component. We measure tensor way. We measure orthogonal components of the magnetic field and electrical field. So the magnetic field represents the primary field response. And the electrical or telluric component represents the response from the ground. So based on the Maxwell equations transformation, we can come to the definition of the apparent resistivity, which is the ratio between the orthogonal electrical and magnetic components. And further calculating, there's a effect called skin depth. And skin depth is the estimation of penetration, which depends only on the apparent resistivity and the t as a length of the waveform, or inverse to the frequency. So on the picture, you can see the basic principle that in the media with the same apparent resistivity, with the different frequencies, we get different depths of sounding. Now we come into the UMT. UMT is a definition which we brought in Phoenix Geophysics. It's called ultra wideband magnetic tellurics. Let's talk a little bit historical now. From the beginning, there was a definition of magnetic tellurics. There was separation to audio magnetic tellurics, magnetic tellurics, and subdivision of long period. The first separation to those divisions was made because of the source of the signal. but also because of technological capabilities at that time. The technological capabilities, the hardware which was available, or chips which were available, calculation, also the space of the memory, and others. And at that time, it was not reasonable to collect the magnetic telluric signal to acquire the audio magnetic tellurics, and vice versa. Later, with the time, it was introduced the method called BMT, or broadband magnetic telluric. The broadband magnetic telluric was something between the audio magnetic telluric and magnetic telluric, and it was brought approximately 10-15 years ago with development of technology of manufacturing or constructing the magnetic sensors. I'm going to talk about magnetic sensors a little bit later. So now let's describe a little bit more. So audio magnetic tellurics covers from 10 kilohertz down to approximately 10 hertz. And this data, depending on the apparent resistivity of the media, of the ground, it gives us the measurements from about 50 meters down to probably about 2 kilometers depth. The magnetic tellurics itself goes from 300 hertz and goes down to, we'll say, 10,000 seconds. And this gives the penetration from about 300 hertz down to dozens of kilometers. One remark is that in magnetic tellurics, we call all frequencies above 1 hertz, we call in hertz, and all below 1 hertz, we call in seconds, which is the length of the wave, because it's easier to say 10 seconds than 0.1 hertz. Or when we talk about 1,000 seconds, it's easier to say 1,000 seconds than 0.001 hertz. So in the long period method, it's a little bit separated subdivision of magnetic tellurics. When the studied the frequencies which starting from about 20 seconds or 0.05 hertz and going down to approximately 50,000 seconds. Those studies are related to lower crust and mantle studies. This depth starts about 30-35 kilometers and goes down to hundreds of kilometers. So now in Phoenix, we developed the new magnetic sensors, and the magnetic sensors is one of the most important part of the system. So the new magnetic magnetic sensor, which covers full or ultra wideband range of the frequencies from 10 kilohertz down to 50,000 seconds. And this device works without any switches. It collects the data on ultra wideband range in one recording. So what do we need for to measure magnetic tellurics? It's as we just were talking, the magnetic sensors. We need the electrodes. We need the receiver. We need the software, and the most important, we need time. A few more words about magnetic telluric sensors. There are quite a few different sensors which provide a different frequency range, and the most of sensors which provide wide frequency range is basically two sensors built in one housing, and there is a so-called chopper. So with turning chopper on, we can measure the MT signal. With turning chopper off, we can measure the AMT signal. This chopper can be physical or electronical, but this means that it has to be switched. So we can't, or we have limitations on acquiring the data at the same time. So we will separate the AMT and MT band. In the new generation sensors, which Geophysics developed, there's no chopper. It's unique technology providing the full band, access to full band in one recording. Just for your understanding, that when we talk about 50,000 seconds, this is a very long time recording. Remember, I told about time. Just for your reference, about one night recording of the magnetic telluric signal, depending on the ambient noise, gives between 500 to 1,000 seconds data. To record 10,000 seconds response, we measured that should be 72 hours of the data. Just for reference, 10,000 seconds is about 1.3 hours. But 1.3 hours is not the data, so it requires much more than 3 hours. So 72 hours, but it should be very quiet 72 hours, preferably at night time. So therefore, by our experience, to record 10,000 seconds, the system should stay about a week. We had the experience recording 20,000 and 30,000 seconds. In this case, the data acquisition should stay, the data acquisition station should stay about 21, 24 days on the same place. So one of the important parameter of the magnetic sensor induction coil is the noise floor. So on this picture, you can see the orange line is the natural signal, and the blue line is a sensor called MTC150, and the red line is a sensor called MTC180. We can see that MTC180 is a little bit noisier on the lower frequencies, but MTC180 is a little bit shorter. In certain situations, it's preferable to use the shorter sensor. Now, when we talk about acquiring data overnight or over several nights on several weeks, we have to eliminate any movement of the sensor. The sensor should be very, very still and quiet. Therefore, we bury our sensors, because even the wind movement will disturb the data, will create additional noise. So, and also when we dig our sensors in the ground, we prevent high gradient of the temperature changes. This is very important to the places which have very big gradient between day and night in temperatures. The new sensors have the temperature stabilization, but still, if we can reduce the gradient of the change of the temperature, this is better. And the third thing is the calibration response for all magnetic sensors. All magnetic sensors have a certain response to different frequencies, and therefore we have to know what is the response, what is the calibration of the sensor. This curve allows us to convert the millivolts, or which we acquire from the sensor, to nanoteslas. The next two pictures are two examples of our comparison of the sensors, the induction coil, this MTC150 induction coil, and the flux gates sensors. Which the flux gates are smaller sensors they used for the long period observations. So in 2017, we did the comparison of MTC150 with the LEMI flux gate. We recorded over 560 hours over 20 days. And you can see the solid line, the thin solid line. This is the LEMI flux gate. You can see the data starts from about 20 seconds and continues. There's reasonable data goes down to approximately 20,000 seconds. And the response from MTC150 is very identical on the lower frequency range, but also provides the high frequency range, which is not possible to acquire with the flux gate. And just for your to remind you, this part is about 30-35 kilometers of the ground. We have repeated this similar test with the Bartington flux gate in 2019. We recorded over 24 days the data, and you can see the same, like the flux gate starts on the data reasonable starts about 20 seconds, and here we measured the signal down to approximately 30,000 seconds. And same situation, you can have similar response on the lower frequency range, and no response from the flux gates on the high frequency range, but the response on induction coil. Why this is important? Because previously, about 10 years ago, there was believing that the induction coils cannot measure very long periods. So we could prove that this is not like that. Now we go to the electrodes. So the electrodes, for certain surveys, you can use like standard steel stake electrodes for the AMT surveys, for example. But when we come into the frequency below 10 hertz, and especially below 1 hertz, this steel electrodes start polarizing. There's an effect of contact between the steel and the electrolyte underground, which creates polarization. So means the data becomes very noisy. And so therefore, in magnetic tellurics, we use the non-polarized electrodes. The structure of non-polarized electrode is the container with the porous bottom. The container is filled with the salt of the metal of the electrode, and there is a metal electrode inside. There are known very popular 3 types of electrodes: the copper sulfide, lead chloride, and silver chloride. Having a Russian background myself, all Russians love copper sulfide electrodes. But the copper sulfide electrodes are very good for short-term data acquisition. Because first of all, copper sulfide electrodes, the copper sulfide tends to dry, and they have to be refilled often. But secondly, when the copper sulfide crystallizes, the crystals become very, very large, and they plug in the porous membrane on the bottom of the electrode, preventing the capillary connection between the electrolyte and the solution inside the electrode. So they have to be maintained very often. They have to be washed and refilled very often. The silver chloride electrodes, I never had myself experience working with silver chloride electrodes, but besides that, they are more expensive. They also require quite a lot of maintenance. We found that the lead chloride electrodes are the most stable in this case, and the last P5 generation of electrodes, we built them sealed, so they cannot be disassembled. They are disposable, about 2 years of use, and then they have to be exchanged. Why we don't open them anymore to refill? There are 2 reasons. The previous electrodes were refillable, so why we don't like that to do? There are 2 reasons. First of all, when you have refillable electrode, you have to have chemicals with you in a small bag, which limits travels, because everywhere you're going to be asked for the chemical declarations and approvals and safety. And secondly is complicated. And the second thing is refilling of electrode in the field is a very tricky operation. Quite a few years ago, we had an experience when some of our customers called us and said that the data doesn't look good anymore below 1 hertz. And we asked them what did they do, and they said, well, we'll refill the electrodes. We asked, how did you do? Yeah, we just took some water, we added some water. And the point that electrode is as important in the magnetic tellurics survey as the magnetic induction coil. If the electrode is bad, the data will be bad. So therefore, refillable electrode is something which we cannot control. We cannot provide the quality of that. So therefore, the decision was to build the non-refillable electrode. More than that, there is not a liquid inside the electrode. There is a suspended solution of lead chloride, and this suspended solution, it looks like a gelée. It's not a gelée, but it is like gelée type. So it's not leakable. It doesn't dry very fast, and the membrane, porous membrane at the bottom has a dual layer to prevent leaking of the electrode. So they are showing low noise, low drift, and their lifetime is up to 2 years. The next point is the receivers. So the new receivers are built from the aviation grade aluminum. They are machined from the aluminum part. You can see on the picture on the right, there's only one seam. So this helps us to seal the box to improve its waterproofness and dust proofness. It has the military grade connectors, and it has a display for the independent operation, so we don't need to connect any computers to start the box. And we have also we use the SD card as the memory carrier, and SD card can be up to 512 gigabytes, so the size of the memory is not a problem anymore. Besides that, the new system is based on all new chipset, and it's allowed us to reduce the power consumption to below 6 watts, which is about twice better than the previous generation's equipment. On this small video, I will show you what the screen, the small LED screen, shows when we start in the system. Right now, you can see that the system is idling. There is a message idle. Once the system acquired the GPS position and GPS timing, it goes to the idle mode. Then we start, and it goes to the self-test. During the self-test, it runs the testing the auto DC shift in the channels. It corrects for DC. It runs the MAC test. It verifies that the magnetic sensors, the magnetic induction coils, are what the system expects to have. Then it runs the resistivity of the contact resistivity of electrodes, and once all this done, oops. I apologize. Then the system goes to the data acquisition mode, and at this point we can go through the screens through each channel and make sure that all channels showing what is expected. For example, the last channel showed the magnetic channel, and it shows that the configured induction coil is MTC150. The detected induction coil is MTC150, which means good. The AC value, DC value, and the saturation. Knowing this information is very important before leaving the system to record overnight or over several days, because the worst thing is coming after recording is finished and finding out that something was wrong or something was not set up properly. So all receivers before all systems before sending that to clients, we test, and first of all we test on the temperature in the temperature chamber. We test all systems from -25 to +55 ambient temperature. And on this picture, you can see the receiver inside the temperature chamber. And this is not the dust, this is the frost on the top of the receiver. And this test, we don't do this test every time, but it was a small experiment. We put one of the receivers into the aquarium and started pouring water. And you can see that the LED lights are blinking, confirming that the system is working. This is the waterproofness is very important for the equipment, which we can live for several days in the field, because probably in Brazil also the rain is an issue. In Canada, when we set up the very nice site in the evening, we come in very often in the morning and it's a big swamp because there was a rain overnight. It will be very sad to lose the system because it got flooded. Just one remark, those receivers are not the marine receivers, so they are not made to work underwater. They're just made to not fail during during the flooding. Next question is the time. The time and the important time is a sampling mode. So you remember we collect the data on a high frequency like AMT and MT and long period. So when we collect the data, we record with certain sampling the data to the card, and for sure it fills up the memory. The system like MTU5C system can collect in continuous sampling modes. So it means that we will just start the system and continuously samples on several frequencies on 24 kilohertz or 24,000 samples per second, 2.4 kilohertz or 150 hertz. 24 kilohertz, this is upper sampling rate. To achieve 10,000 hertz response, we want to sample at least twice. We want to have at least twice higher sampling rate. But 24 kilohertz for 5 channels will give us about 1.4 gigabyte of the data per hour, which is a lot. So for that, we developed the sampling modes. If you have any experience with working with MT, with older equipment, you know about the startup timing tables. The timing tables was pretty sophisticated part of this installation of a magnetotelluric system. We had to calculate when, which frequency, at which time will record. And the idea of timing tables was to minimize amount of the data collected on each frequency to have enough for the to process that, but not too much, not to overfill the memory carrier. Right now, because we have no problem with the memory, because as I told you, SD cards, which the minimum SD cards which we use is 64 gigabytes. So therefore, we set up only 3 modes. The first mode, actually in the center here, we call high sampling mode. It continuously samples on 150 hertz to resolve all lower frequencies bands, starting 75 hertz and lower. And it does a sparse sampling of the higher frequency. In this case, it's 2 seconds per 30 seconds period, or 4 seconds per minute. And this sampling of the high frequency is distributed evenly during whole sampling period. So if we set up the station to record the data overnight, our AMT data will be collected overnight, not only at the one point of the night, like in the evening, in this case. In this case, we're going to collect about 130 megabytes of data per hour. If for some reason we need to reduce the size of the data, we can set up on the low sampling rate, where we collect the high frequency mode 1 second per minute. In this case, we're collecting about 40 megabytes of data per hour. And for certain long-term operations, we developed another more complicated schedule. where we continuously sample 30 hertz, sorry. We sample mid frequency 2.4 kilohertz, 20 seconds per 10 minutes period, and 1 second we sample on the 24 kilohertz per 10 minutes period. In this case, the data size is reduced to 10 megabytes per hour. The other feature, which is not the feature, not the option, but the standard part of the each MTU5C receiver, is the networking capabilities. Just by connecting an external modem, we can convert any receiver to a monitoring station or to a remote reference station with network connection. Why is this important? Because it was like, first, in the monitoring situations, we can leave the system for a long time, and we don't want to go to the system every time and check the data. But the more common case is using the remote reference. The remote reference technique was introduced in late 70s. It comprises the use of the one dedicated station as a remote reference, which sits in the similar primary field conditions, but very different noise environment. It might be 10 kilometers away, it might be 100 kilometers away, it might be several hundred kilometers away. In the case when it's hundreds and more kilometers away, we don't want to go there every time to collect the data from that physically. So we can set up the networking and collect all the data in quasi real time on the server. So we don't develop the modems, and it's not our business to develop the modems. So therefore, we don't build internal modem, because the internal modem will be too much for certain operations and not enough for other operations. Therefore, we just developed the possibility of connecting any commercially available modem which corresponds to your project requirements. You can connect that, you can program that, you can select your data plan, which the modem can be satellite modem, GSM modem, it can be Wi-Fi modem. You can select your data plan and you set up your own server. The previous generation equipment on previous monitoring stations, they required extensive server support from the company, from us. Now we don't touch your server. You configure your server, like there's pretty standard configuration, and then your data is your data on the server. Nobody has access to that except you. And this is important because in many countries, I'm not sure about Brazil, but in countries like China, India, Russia, and many others, it is restricted to have access from outside of the country to the geophysical data. So once we configure that, there's a very simple configuration on the receiver side, and the receiver will stream the data in quasi real time to the server. Quasi real time means with accessibility of the bandwidth. So if there's enough bandwidth, so it streams the data. If there's a network down, it collects the data on the SD card, and once the network is back, it starts streaming the data again. The processing software, the last part of the system which we're talking, the previous generations process software were consisting of a lot of applications. Now it's only one application which does everything: preparation, evaluation, and management of the data. Again, like the processing of the data was previously required to save the data in certain folders, then connect different folders, and then process that data from different folders. Today it works as the graphical interface with a database approach, with a project management, when we can have up to 3,000 stations in one project. We have full access to metadata, multitasking, remote reference, and stuff like that. And all this I will show you in the a little bit later, because this part of the presentation is done. If you have any questions, you're welcome to ask. I will very quickly show you the field installation of the system. We went to the field because right now it's pandemic. It's very difficult to show it's in live. So we went to the field and recorded some videos for you. So there are some typical operation of the one night data acquisition. We bring the system in the field. We run the calibration of the receiver. We run calibration of the sensor. We prepare the station location. We set up the system. We record the data. In the morning, we come back, collect the system data, and we clean the site. So the receiver calibration, it is important to run time to time the receiver calibration to make sure that everything works correctly. It takes only 10 minutes. It's very simple. We prepare the calibration task for the receiver. We save it on SD card. We set up, we can do actually the receiver calibration even in the office. The only thing which is connected to receiver externally is the GPS. So the receiver checks all the paths inside, all the channels inside the receiver. Very basic, what's going on when we start. Then we can see what's going on the screen. It shows us just the receiver calibration. So, and takes 10 minutes, and then it stops. The next part is a sensor calibration. Sensor calibration is something which has to be done in the beginning of the survey and at the end of the survey. And we suggest always to do it periodically, maybe once in 2 weeks, maybe once a week, depends on your survey. It's a way to confirm that your sensors are working correctly, because transportation and other actions can damage sensors, and then it will be very unfortunate finding out that the sensor was not working properly after the data being acquired. The sensors which we built, they support the field site calibration. So what's going on, actually, the receiver sends some test signals to the sensor, and the sensor then collects the response from the sensor. Again, the software part is, again, we just prepare the sensor calibration. We enter the serial numbers of the sensors which we want to calibrate, and we save this to SD card. The system installation, because as I explained to you, the sensor calibration comprises some kind of active field, so it's not very sensitive to external noise. We don't have to dig it underground. We can just lay out on the ground. If it's very windy, then we will prefer to maybe to dig it underground, to bury it. But usually we set up on the ground, and it takes about 30 minutes, and then we have the data. So once we set up the sensors, we connect all them to sensors to the receiver. We start the receiver. We start the calibration, and you can see in 1 second it shows the sensor calibration. So very simple. Sorry, and oops, there is one more layout which is not very often used, but it's a very powerful layout called parallel noise test. The parallel noise test may be used to estimate the quality of our system setup, and also the noises in the area. The parallel noise test is when we set up all the induction coils and the E-lines parallel to each other, orthogonal between them, and we just run for like extended period of time, maybe for overnight, to see what the noises are between the sensors. The idea is that the with a same external signal, the different sensors have to acquire the same signal, and the difference between them will be the noise. The noise, it will be the noise of the, like in this case, like the sensor, plus the noise of the channel, plus if there is a very extensive external noise, electromagnetic interference, it will show as well. And the standard as an orthogonal configuration, the orthogonal configuration also is very easy to prepare. We just select the magnetic telluric in the preparation window. We select the timing. We select the channels. We describe the all channels. I will show you a little bit later. We set up the orthogonal station. So we have the orthogonal E-lines, north, south, and east, west. In our case, the positive is north and east directions. And we set up the magnetic sensors. We usually set up the magnetic sensors in different quadrants to avoid any interference between them. But they can be set up as close as maybe a sensor distance between two sensors. So our positive direction is east, north, and the vertical component looks downwards. Yeah, and we bury it underground as well. So once we start the acquisition, this I actually already showed you. I'm not going to repeat. That is the same what we saw before. Some layouts tips. Sometimes we cannot lay out the system like bury the sensors. In this case, we have the idea to use the heavy blankets, heavy rubber blankets. Again, we don't try to invent the blankets. Those blankets can be found in the hardware store. We created the solid channel for the sensor, and we covered it with a blanket to avoid the wind movement. For the vertical sensors, sometimes when there's no possibility to dig it completely underground, we might put like 2/3 of the sensors on the ground and have the remaining over the ground. In this case, we will build for the over the ground sensor. We will build pyramid from the ground or rocks, also to prevent any movement. Okay, this one was a short. The next one, I'm going to show you the live work of the EM power. We'll go with the management of the data. I'm not going to go review right now the prepare and evaluation modes. When we manage the data, we can select from existing project, or we can create the new project. I will select the one of the existing projects. So this the data which was collected in Saskatchewan is one of the central Canada provinces. Just going to give you a little bit of reference. This data was collected for the University of Saskatchewan, located in Saskatoon. One of the students was
não começou mesmo, não. Ele consta como aguardando. Só um minutinho, tá, gente?
Gente, eu tô achando que foi para outro link. Eu cliquei para, pelo menos eu entrei no canal do Observatório Nacional, tem um outro título com a nossa imagem aqui. Tá tipo Ciclo de Seminários Geofísica 2021. Tá sendo lá reproduzido nosso ao vivo.
Só um minutinho, tá? Só um minutinho, que eles estão acertando, vão ter que reiniciar aqui, talvez. Vai ter que reiniciar a transmissão. Eles estão tendo que refazer. Eu vou desligar aqui o áudio, que ele me mandou um áudio, eu vou ouvir o que está acontecendo. Aguarda só um minutinho que eles estão tendo que recriar a live, tá? Só um minutinho. Mas não sai daqui, não. A gente não precisa sair daqui, não, tá? Só um minuto. O Vitor, tem que usar aquelas... Tem que ver com o Rodrigo também, né? Vitor? Gente, alô, alô a todos. Olá a todos, estão me ouvindo?
Eu tô
Sim,
aqui.
estamos.
Tá. Ele vai ter que criar outro Zoom, então a gente vai sair desse. Eu vou passar para você, Rafaela, outra link do
Aham.
Zoom, e para o Rodrigo, e para o Roig, e para o Vitor também, tá? Vamos sair dessa, ele
Sim.
vai criar outra, tá?
Ok, aí eu
Ok,
encaminho os
José.
grupos.
Obrigada.
Tá bom.
Desculpe aí, viu, gente? Houve um conflito lá. Nós derrubamos a live dos seminários, estava acontecendo.
Ah, ih,
Eu imaginei, eu tava vendo aqui.
tá. Então saímos aqui? Sim.
Okay, return now. Okay, Anton. Anton?
Yes, sorry, my mic was off.
Okay.
So I can continue, yeah?
Okay.
Okay, good. So we were at the point of the strengths of the signal of the magnetic sensors, and we can see here some drops. So there's additional column is called saturation, and we can observe what was happening. So at those points, we had the saturation of the signal. I can explain why was the saturation, because we were working, this night we stayed at the site. We set up the site very late the first night, so our vehicles were staying somewhere here. So while we were traveling back and forth, so we saturated the sensors because the sensors were close to the road. But like you can have some other events which saturate your sensors, and it's very good to know when they were saturated. Okay, so beside that, we can always have some attachments. I don't have here any, but we can add the pictures, we can add the logbook, copy of the logbook, because we always want to have the logbook in the field. We have to put all the notes if something is going on or happening. So we can see our time series response and work a lot with the data. One of the things you can note here is the green check marks. the green check marks, it means that for those sensors, there is a field calibration available. So if I change, for example, the serial number of sensor, the system will say there's no field calibration for the sensor. In this case, the system will use the generic calibration curve, but we always prefer to use the field calibrations. We can have access to each sensor calibration from here, or we can go left top to the calibration viewer, and we have all sensor calibrations in the same window then. Why do we want to use the field calibration? Because if you pay attention on this area on around 10 kilohertz, when I jump between sensors, there's a small variations on the high frequency. Those variations are related to the physical winding of the coil, because it's nearly impossible to make identical, completely identical. It's like with a good wine, you can have same year of the wine, but wine from different barrel will be tasting a little bit differently. The receiver calibration shows all channels of the receiver, and they have all identical calibration, which is good. It should be 1 everywhere except the very high frequencies. Those lines are decimating points, and they not applied during processing. So we have to have 1 line here. We can always export the calibrations if we want to process data outside of the EM power. So the next part is the processing data itself. Just before that, I will show you another station, the elbow 1. The elbow 1, if you can see, had only 2 dipoles in an L shape, because I didn't want to cross the road, and no magnetic sensors. If you remember a little bit earlier, I was telling you about that magnetic field represents the primary field. So it is more homogeneous or similar on certain area depending on the frequency. So the magnetic channel can be shared actually between neighborhood stations. And that's what we're going to use. We're going to use the magnetic signal from the station elbow 2. And we're going to process the station elbow 1. Opens the dialog. We select the station. We select the electrodes. We can, in case we have more electrodes than 2, or we have somebody connected them differently, we can always reset that. We select the magnetic sensors. This system says there's no magnetic sensors on this box, on this receiver. So we're going to use the neighbor one from elbow 2. Then it asks us if we want to use the remote station. We're going to say yes, our remote station. Then it asks as a time. This is the time when all, in this case, 3 systems were working simultaneously. So we're going to set up from midnight to 8 a.m. And the next point is the nudge filter. It was in Canada, so it's a 60 hertz. I'm going to give a unique name to the station. And it starts processing. And we can see that with the accumulation of the data, of the signal, we can see the changes. The EM Power is a multitasking system. It uses the multi-core capabilities of a computer. So we can close this window and we can process even the same station. I'm going to use again the neighborhood magnetic. But this time I'm not going to use the remote reference tool. So you can see what the difference between remote reference and no remote reference signal. Till 8 a.m. So, and you can see that actually stations are being processed at the same time. Yeah. So a little bit while it's processing, I'm going to tell you a little bit about the magnetic telluric response. In Brazil, the response is a little bit different than in Canada. There are, you remember we were talking about the lightnings, which cover the AMT band, the far lightnings. And Brazil is very close located to the epicenter of the thunderstorms. There are 3 around the world. There's Brazil, Indonesia, and one more. I don't remember right now where. So therefore, in Brazil, for example, the data in the AMT band is much, much cleaner than in Canada. In Canada, we have the issue with so-called AMT dead band. Where's my mouse? Which happens in area of 1 kilohertz. And also everywhere we have the issue with the MT dead band, which happens around 1 hertz, but it's very wide between 10 hertz and 10 seconds. And one of the methods to remove the MT dead band is idea of the remote referencing. So what happens is we have because the MT dead band is very depends on the, like both AMT dead band and MT dead band are caused by the low signal in this range, and therefore the noise becomes very significant. So if we have the remote station which has a similar primary field but different noise signature, then by comparing the signal, the system can identify what was the noise and remove that. But this remote reference which we use here was not very great. It was only 5 kilometers away, so it didn't clean very well. But we can go right now to the process data. We can see our data here, our 2 stations, the one without remote reference and one with the remote reference. So what we did right now, we just calculated the apparent resistivity curves. So it's not the data which you want to work unless it's very clean from the start. You want to add a couple touch-ups to this data, and it's called denoising or cross-power editing or robust processing, different names for that. What we're going to do, we're going to take right now the station without a remote reference, and we're going to make it prettier than the one with remote reference. So the, sorry, I just have to move. Something on my screen is blocking me. Oh. So this area, the denoising area or cross-power editor, we call it a workbench. The idea is that we create the workbench and we have several tools, and it's like on a workbench. When you work with something, then you leave your tools in certain orientation. Then you can come back to the workbench, to the same workbench, just like put the tools in different orientation, and you're going to have same workbench but different view. Here we can work with the resistivity, with impedance. We can define the rotation angles and stuff like that. And those are our tools. We have 3 types of masking: the time masking, the amplitude phase masking, and the robust masking technique. We're going to start with the time masking. The idea of the time masking is that we have good data and we have a bad data. If we combine them together, we're going to have a bad data. So we want to just exclude the parts of the data which were bad. So what on the right lower corner, we can see the time representation, time editor, time representation of the collected signal. Those are the cross powers or the signal at each moment of the data acquisition. We can see that we started from the midnight. We still had some evening influence of the very strong noise, and we're going to mask it out. And I will also a priori mask out the morning influence. now, using the magic tool, 2 fingers, I'm gonna, with 2 fingers, select the hotkey, combination of hotkey. You can see right now on the screen the help. So it's going to be the shift and the arrow. And I'm going to copy this mask to the neighbor frequencies. Voila. The deadband, empty deadband, we removed empty deadband. Now we go to the AMT deadband. It's not very significant here, but the point that AMT deadband has a little bit different nature than MT deadband, physically different nature. And if we're going to start, the AMT part is more influenced by artificial noises, because 60 hertz or 50 hertz and harmonics, this is where the AMT signal is laying. So therefore, it will be much trickier to eliminate the noisy, separate noisy and not noisy times over the data acquisition. And I don't like to use the time masking when I have to make very fine, select very fine parts of the data. So I will use the amplitude phase mask in this case. So the amplitude phase mask is this polar diagram on the upper left, right. This is what we can see with the signal. So we can see the signal is actually pretty strong and aligned, but we can see quite a lot of points which are jumping out of, which are out of phase. What we're going to do, we're going to remove those, restrict those like out of phase signal. In this case, we're going to select this part. We're going to strict the YX phase and strict the XY phase. And now again with the shortcut hotkeys, we're gonna use a control and arrow, and we're gonna copy this amplitude phase mask to neighborhood frequencies. So, and voila, we removed both MT deadband and AMT deadband. You remember I told you we're working like with the database approach with the data. We can always bring it back and add. And I'm going to show you in 1 second what's a robust processing technique. Those algorithms are developed by Alan Jones, somewhere late 70s. It uses different coherences approaches. I'm not going to go very deeply. I'm just going to put some coefficients just to show you as an example. It's also the way of eliminating, separating the bad data and good data. It works pretty good for the MT deadband. It still leaves some things which not very pretty, and in this case didn't do anything with AMT deadband. Again, we can always combine with other techniques, and we can sometimes remove, because in our case, actually, with the time and amplitude mask, phase mask, we could clean the data pretty good. In this case, fortunately, was very helpful because it was 1D geology and low noise. So it's a very nice example of the data. Now we can close that, and we can take our data and we can superimpose our data and edit it. And like, let's put also the station with the remote. So this is our unedited signal. This is our signal of our station with the remote, and this is our edited signal, which we just made right now. In this case, it was pretty nice. Like 8 hours of data we edited like in 5 minutes. And then after we select what station we consider to be good, we can say, yes, this is one approved. And then we can just take and export that to ETI files. and then as output, we're going to have EDI files, which we can import into 1D or 3D processing and process outside of the this part. I'm done with the EM power. Do you have any questions about equipment or EM power? Well, I hope not. That's good. So now I will have, yes. Any questions?
Have questions.
Good. I like questions. Yeah.
It's possible open your video, no problem. And Carlos and Williams too. I think I have one curiosity, and I don't exactly specialist in your area, but in your opinion, what is the source of noise more important in the MT and this equipment?
All noise is a noise.
What is more important for
okay,
example, conductivity, soil, or rain?
Well, this is one of the point of the magnetic tellurics. If it was like what I showed, it looks very simple and easy. And if it was the very simple and easy method, then first of all, nobody will pay for us to use this method. And secondly, everybody will use it all the time. It's a very sensitive method, yes, because we investigate or we study the natural electromagnetic field, and we have all noises possible are did I stop? Oh, did I stop sharing? Oh, no. sorry. I was like by mistake turned off. Okay. So all noises are becoming our noises, and the moving. So the moving of the sensors is the big noise. So the sensor is the electromagnetic coil, induction coil. If it moves in the electromagnetic field, it creates the signal. So therefore, this why we say we bury the sensors, but we want to make it sure there's no like significant seismicity as well. If we put it too close to the highway, the data will be good. Bad. If we put too close to the like I don't know, like major like railroad, the data will be good. Will be bad. Sorry, will be bad. Yeah. Secondly, the wires. If our wires, like the cables and wires, they will be flipping in the wind or hanging on the grass and moving, they're going to create the noise as well. So for overnight recording, we just tackle all the wiring to the ground with some heavy stones or something. If we put the monitoring stations, we actually bury our wires underground, is the same to prevent the movement. Next thing, the animals. All animals are very curious. They like to test our equipment. They like to test the wires. Our wires have a repellent against certain animals, but the practice showed that the repellent in one country it distracts the animals, but in other countries, other animals are attracted by that repellent. So there's no optimal solution. We have stories, except the mice and all the small animals. The cows choose the cables. The kangaroos choose the cables. The bears, they come and they are curious what it is, and they opening, disconnecting the powers from the receivers just by smashing it. Like all animals, human is a big noise, yeah. So human usually attempt to steal and run away.
Or line, yeah.
Yeah, with equipment, curiosity or idea. So we have to have like security on the site. We have to make sure that the site is kind of protected, or we have to hire the security to the site as well. But if you hire security, they have to be instructed not to walk around the station to. But it's only right now I'm talking about mechanical noises. But now electromagnetic noises, the power lines, the like the railroads. This is very important. The electric fences. More than that, the huge like metallic objects like the pipelines. The pipelines is a big problem. They create the so-called near field. So they are basically, it's not even noise to the system. It's a noise to the field, because pipeline on certain frequency, just all the currents on certain frequency start going through the pipeline, because it's much higher conductivity than anything underground. And we don't, like, for example, we see the near field at like 1 second, for example, frequency, which is probably like about two kilometers, say 2, maybe 3 kilometers underground, and means that below that we cannot see anything below 3 kilometers in this case. And
it's high frequency.
Yeah, we can see only high frequency, but nothing, we can see nothing below. So and also the thunderstorms, local thunderstorms, and a lot of things. So it's a tricky. It's a lot of trials and errors, a lot of kind of acquiring a lot of experience, and making sure that selecting the good site for MT. It's a big story. It's a complicated task.
Okay.
I can see there's quite more questions. I have to answer questions.
Yeah, have La Terra, Emmanuel, have one question, have more question here. He talk. It's possible to download the data during the data acquisition?
If we use the remote data transfer option, like we can download to the server. Right now we can do it only to the server. So if we have the modem, the data can be streamed to the server. Right now we don't download during data acquisition. There are two reasons. Like one reason, just because we don't do it technically yet for the system. But secondly, when we acquire the data, you remember, we need to acquire a couple hours of the data. We're not going to be sitting overnight near the system and downloading the data. Yes. So therefore, this option, like just download to your phone or to your computer directly, is not possible right now. But
it's about battery. He questioned, what kind of the battery is needed for long-term data acquisition? So
the station, as I said, like it's pretty low power consumption. The standard battery, like small battery, like 40 ampere hour battery, lasts about 2 nights, for continuous 2 nights data acquisition. Some of our customers here in Canada, they use some quasi monitoring tasks, like space weather studies. They have 200 amps batteries, and the 200 amps battery, not 100 amps. I think 100 amps batteries. This lasts for them about 2 weeks. They come in every 2 weeks to the station, and they swap the batteries. For the longer terms, we install the some renewable or uninterruptible power supply, such as solar panels. It will be the batteries plus the solar panels. Solar panels charging the batteries during solar like sun time, and the battery continues working overnight, and then the next day they are being charged again. Or for example, in Japan, we have the monitoring station staying in Japan, and in this area where it's staying, in the winter there's about 14 feet of snow, like about 3 meters of snow. It's like very thick snow, so the solar panel is not going to work because they're going to be buried with the snow. We use their thermal generators, like the gas generators, which we fill in the autumn. It lasts on one fill, it lasts like 6 months, and in the summer it works on the solar batteries.
Okay, Leonardo Michelucci say one question here. What kind of new technology allowed Phoenix to develop such a ultra broad range magnetic sensor?
Well, So the point that there is the one important part is the preamplifier, which is inside the sensor, and that's one of the biggest limiting factor, because the preamplifiers, like standard preamplifiers, they give you certain range of the frequencies, and like outside of this range, they are too noisy. We found the preamplifier, which is a ultra wideband, and yes, so this is how it goes.
He talking in terms of hardware.
About sorry.
I'm sorry, my neighbor here have
I heard
long sound. He questioned about terms of hardware. If have a new technology about the magnetic coin.
I don't think I quite understood, and I will try to answer this question later if you can forward me by email. Just in very like general terms, it was like different sensors were tried with magnetic tellurics, and the regular magnetometers, which like the vapor magnetometers, like the cesium vapor or something, or potassium vapor,
have several modifications.
Or the squids, they all too slow. They are good for the very slow data acquisition, but for magnetic tellurics, they're too slow. The flux gates, as I showed you as well, they're also too slow. They can get the data only starting 20 seconds. They're not getting the data high frequency data. So this is one of the limitations. So there's no replacement for induction coils for the wideband data acquisition right now, as far as we know. But I will follow up with this question because I probably didn't understand quite correctly right now. Let's answer right now one more question, and then we have one more part of the presentation, and then I will answer all other questions if we have time remaining. Okay.
Okay.
One more question.
Have more too here.
Yeah. Okay.
What is the sensitivity of magnetic coil?
The sensitivity?
Yes.
Well, the sensitivity, like it's different.
I think in millivolts, Tesla.
Yes, I showed you here in one presentation. So the sensitivity, there's one important thing with the sensitivity, because which is called noise floor as well. The most of the manufacturers are working with equivalent noise floor. So they basically estimate. They have very nice numbers, but they estimate their numbers. When we present the noise floor, our noise floor on our materials, which we present, is always measured. We always measure that. So this is a realistic response from the coil, from measured response from the coil, not an estimated. So we actually had the chance once in 2014 to measure one of the other coils who show a very nice noise floor, but turned out that the measured noise floor is the same like from our coils, so it's not different. But they're kind of advertising, they show a very low noise floor, and the noise floor is different on different frequencies. Yeah, sensitivity is different on different frequencies.
Okay. One more about the MT5C and MT5A. No?
Yes.
What is the advantage and disadvantage?
Okay, so the first thing with MTU5A, it's a 20 years old technology. It was a great system at that time. It's still it's a very good sensitive receiver, but the problem is support of this receiver. It's technology gets old. It's very difficult to find the components to maintain this receiver. The software also outdated. It requires. I showed a couple pictures that were from the older software. It's all was written on the older programming languages. There's we don't have basically the people who can fully support the old software and old equipment. So one of the equation is the support. Second question is the MTU5A had 12 watts power consumption, so twice higher power consumption. It had a much lower capabilities of temperature dissipation. So it was heating up much quicker. So the problem was MTU5A on working in hot weather. You had to very good shield it from the protecting from the sun. The memory size on MTU5A is only 1 or maximum 2 GB SD card, SCF card. So you cannot freely work with the data. You have to collect a much less and tight data. So therefore, MTU5A used the startup timing tables. So you had to program the schedule of the data acquisition. And also when working and processing the data, there were also some limitations. What I showed you with the cross powers, that's nice when we can just statistically eliminate, make the time masking, phase amplitude masking, and we can have access at each frequency thousands of different cross powers. MTU5A was allowing maximum 100 cross powers per frequency. So there we couldn't do much statistic. We could just separate night and day times, but not like exactly like we see there's some influence. We just remove this part of the data, or the phase and amplitude the same.
Okay, William.
I see the questions coming. If you allow me, like I'm gonna show the case history part, and then we're gonna answer other questions. Because depending on the time, is it okay?
Okay, I think it's the last question.
Only. Okay, because I can see that the questions coming.
Yeah.
Okay, go ahead.
Alcides, one guy, the Observatório Nacional, working Observatório Nacional, question: what is the error in the depth for each frequency?
Sorry, what is
error in the frequency in each frequency? If have a range of error.
I don't think I understood exactly.
It's technical.
Carlos, do you have any?
Você me escucha? Você me
Yeah,
escucha?
go ahead. Yes,
Yeah.
go ahead.
What is the margin of error?
Oh, the margin of error. Well, it depends. Like again, if we I still have it open. It depends on the quality of the data. Where we were, I'm gonna show you. It very depends on the data. So here, when we were using the station with the remote, but I told you remote is not very good. So I tried to remove the deadband. You remember our deadband. So with this remote, it was removing the deadband, but the error was very, very high. Yeah. But the way we calculated, actually, the on this area, the error is very low. The error is showing a little bit here because we don't have kind of a lot of information here. So it's not constant. It will be calculated and will be shown on the chart. Okay.
Okay, I think it's okay.
Okay. I think I see there's quite more questions. I'm not reading them because but if there are more questions, we're gonna follow up and answer them after. Okay. So
if have other questions, I sent for you in email.
Sure. Yes, you're welcome. No, so where's my mineral system? Yeah, it's here. So the last presentation is going to be the a little bit the case histories and mineral system description.
I think you have 10 minutes only.
Yes. Okay? That's why I'm trying to finish that. I will be first. I will put some disclaimer. The majority of the work presented here, this is kind of compilation of different works. I was not participating in that, so I can present what I know, but I cannot defend or disapprove or confirm some of the constitutional questions. I will ask not to use this presentation as the reference. If you want to reference, go to the original publications because this is just for demonstration. So the mineral system, there was idea of mineral system was developed long time, and the classical approach was that there are some sources of the metal which go in with some flow, and usually are settling in certain barriers, usually get chemical barriers, and there the deposits are being formed. And based on that, the our classical search for mineral deposits is we go like geology, we find the geological prospective area, then we start putting some geophysics or drilling study from the surface down to the deposit. So we try to identify the deposit from top to down. And this quite changed after this presentation. You're going to see why. So in Australia, it all started in Australia. In Australia, they set in 2004, they set a project somewhere in the beginning of 2000s. They set a project AUSLAMP, Australian Lithospheric Architecture Magnetic Telluric Project. The goal was to study the lower crust and the mantle. So basically, they were not interested in any geological information, like upper crust, not in any mineral targets, mineral exploration targets. But they set up the network, MT network, MT grid nationwide. So you can see this is a coverage of the MT stations around Australia with a spacing 55 kilometers, and using they were measuring long period using the flux gates magnetometers that they got about 30 sensors. And then after, once they acquired quite a lot of data, the Professor Graham Heinsohn from Adelaide University, he and his colleagues, they decided to review the data around the Olympic Dam. If you know, the Olympic Dam is one of the greatest worldwide known IOCG deposits, with like tier 1 deposit with a lot of potential for like quite a lot of years ahead. So we're going back to next slide. So what they did, they took the data, this MT log period data, and they ran some 3D inversion of that. And what they could see, there is some deep conductivity, kind of bulb on about 30 kilometers depth with certain isometry. And here's this Olympic Dam, and underneath of the Olympic Dam, there's like very resistive, actually, bulb or something, like the area very resistive. But you remember we were talking that because long period does not have a sensitivity on the on these depths, like from down to 30 kilometers. This all not very sensitive, and all calculations here are kind of approximation, and they are not accurate. So with a lot of talking about that, and in 2014, finally they decided to run the broadband magnetic tellurics. So they set up first around the Olympic Dam the broadband MT with 5 kilometer spacing. And one remark, like the pictures which I've used here, I used the pictures from their publications, so therefore they a little bit different scale. Just to help you with the scale, this we have on the first picture, we have 50 kilometers depth. And then on the bottom picture, we have the depths up to 180 kilometers. So the area which we are comparing is this one, if you can see my mouse. And by making 3D inversion of the broadband data, they could see very nicely this high conductivity bulb. And they can see the roots which come into the Olympic Dam and to some neighbor known deposits like Volcan, Acropolis, and the other, and some unknown deposits as well. And if you look on that, if you can see my picture, it looks like a hand. So it was, those roots were called fingers of God. And based on that, and a few examples I'm going to show you after, they published the mineral system approach, mineral system concept approach, and it was published in Nature in 2018 by Graham Hansen and his colleagues. And this is a new approach of understanding the mineral system. In few words, the approach right now is that there is certain fluids which are pushed, like the mantle with the heat heats up the lower part of the crust, and those melted or semi-melted fluids, they start pushing upwards, and through all the cracks they come in and accumulate in some called fluid chamber. And this fluid chamber is usually somewhere like about 30 kilometers depth, and which we see as a deep conductivity zone. And from this fluid chamber, the high pressure, high temperature, this melted or half melted mass is accumulating, and then it's at certain times it starts going through the any possible cracks or faults or dead faults, and goes to the surface. We know that example is a volcano, but it's not always the volcano eruption, but it's very similar. So it goes upwards, and at certain depths, about 10 kilometers, when the pressure starts releasing and the temperature changes, the crystallization forms the ore deposit. And this process, this is picture from the another publication. The process happens like this is more visual, like this fluid chamber, and there are certain cracks in the air in the earth, and it goes up, pushes up, and then the question how much erosion of the surface is happening. So in this case, we have some deposits very close to the surface, some deposits are deeper. This process can happen multiple times. It's not a one-time process, so it can happen multiple times, repetitive. For sure, it will be very difficult to develop the concept using only one deposit, because it can be said, well, it's coincidence. So the next, they took the data, they took survey in Western Australia. First it was South Australia in Olympic Dam. Now it's Western Australia, the Yilgarn Craton. They put the magnetic tellurics here as well, broadband magnetic tellurics, and they have a similar picture. They have the depths, about 30, 40, 50 kilometers depth conductivity, which is a fluid chamber, and the those fingers of God, which go into some known deposits, and some deposits which are not known yet. Next one is Queensland. It's a completely different part of Australia. This picture is only 20 kilometers deep, so we don't see the fluid chamber, but we can very nicely see those fingers of God. One of them going to the Ernest Henry IOCG deposit. That's Mount Isa in Queensland. So the main idea of this national MT grid approach or study of which we can take from that is a study of mineral system, and mineral systems changes our approach to mineral exploration. So we would now like search or explore for minerals not from the surface to the down, but from the bottom up. So the idea, if we can find first the mineral system and see where those fingers of God are pointing, then we can define the prospective areas where to look for the mineral deposits. I saw one of the presentations. Unfortunately, I don't remember who was presenting. The person took one of the pictures of mineral system and laid over the drill holes for the last 40 years. And the majority of drill holes, which were empty, were actually located there where there's no evidence of mineral system. So in the empty area. So with knowing the mineral system, those mistakes wouldn't be made. What we know, we can learn from the Australian experience. We have to push our governments to develop national grid, MT grid. it cannot be done by private company. It's a national scale, nationwide. It should be done by government. We should use not long period study only, but we have to use to broadband or ultra wideband measurements, which will give us information from the surface down to depths instead of just having the deep information. And the focus of those MT grids should be on discovering the mineral systems. And once the data collected, the data has to be made available for investors, because this is the way to bring foreigner invest deposits. Because the investors are more likely going to invest in a known area than unknown. So now we go to the United States. United States, for sure, they have a similar project. They first had the project called US Array. It's a natural seismic or passive seismic grid around the United States. And then there is a project EarthScope, same long period stations set up together with passive seismic stations and covered most of the US. One of authors or presenters, Benjamin Murphy, I took from his presentation. I don't know where exactly this location, but it's one of the ISG deposits. He put the data from the national grid and he could invert that. We can see there is this conductivity bulb on about 30 kilometers depth, which probably the fluid chamber, but we don't have any information on top because the long period measurements don't resolve this information. So again, from his presentation, if the the broadband MT was used, then we could find the mineral system. Right now, the United States, they acquiring actually the pool of broadband equipment, which is going to be used for different academic studies, but also to repeat some of the stations from the US Array. Canada. Canada is a smaller budget, so we made only Ontario whites. If you know, there is a Sudbury. It's about 350 kilometers north from Toronto. There is a like a ring of fire or green belt area province, which is very rich on the sulfides and graphites. And in 2017, there was set a project called Metal Earth, study of generation of those deposits to understand how it works. This project is still ongoing. It's going to be till 2024. So the information is still preliminary. But from the MT which they use, we can see the deep conductivity on about 20-30 kilometers, and we see some evidence of the roots going upwards. They didn't publish yet final results. We can see some evidence of mineral system, but they're probably going to wait a couple more years before publishing more information. They want to compare with right now with magnetic gravity and other methods which they have. One additional thing which we did actually with the data. So this is about mineral system, which we are talking right now. The additional part which we worked, we modeled the Olympic Dam with 44 by 40 kilometer grid. So what was the purpose? Because we put the magnetic telluric stations like 5 kilometers distance, or like 2 kilometers distance. A lot of people say, well, you guys are going to miss the conductor, because if you put like 2 kilometers apart of the stations, the conductor might be between. But the magnetic tellurics is multi-dimensional method, except what we were discussing before that as a depth apparent resistivity curves. We measure the magnetic vector because we measure all components of the vector. So, and by calculating the induction vector, there is observed that the induction vector points towards the conductor. And we run the model 40 by 40 kilometers around the model of the Olympic Dam. The conductivities were taken from the Auslam project. and it's just different frequencies here. But we can see that the most important are those arrows, which are the induction vectors. We can see even like about 20 kilometers, 40 by 40, about 20 kilometers away, the induction vectors are still pointing towards the anomaly. So this just answers that with the magnetic tellurics method, we can, if we didn't get exactly over the mineral deposit conductor anomaly, we will see where it is located. And there's actually one of the methods, the idea, not very popular, but the idea is induction vector profiling. So people set up only the magnetic components, and they measure, for example, on this station, they look where the induction vector is showing, and they set up next station in the direction of this induction vector. And they basically kind of following the induction vector until they're going to come to the anomaly. This is the idea. It's not very popular. Probably realization is not that easy, but this is one of the dimensions of the method. And I think I'm out of time. I presented the mineral system. That's what I wanted to do. I'm done.
Okay, Anton, thank you very much for your disponibilization here in the ciclo de seminários do Observatório. Obrigada por todo mundo que assistiu, e qualquer dúvida que vocês tiverem, que quiserem perguntar, pode me enviar, eu envio para o palestrante para eles responderem a você. Próxima palestra, dia 26 do ciclo, com o professor Fernando Lopes, da Universidade de Coimbra, que também nos apresentará sobre caracterização morfoestrutural do bordo-oeste do Planalto Central de Huila, sudeste da Angola. Obrigada a todos que participaram. Thank you very much one more time.
Mm-hmm. Thank you very much. And if you have any questions, please send it to me, and we will try to answer all the questions. And well, thank you for without you, it wouldn't happen.